Vidyala Resources present innovative next-generation technologies in treatment of water and wastewater from municipal sewage and industrial waste and recycle the treated water. The statistic as per the government given in Parliament on May 28, 2019, the country generates 61,754 mld of municipal sewage from urban cities against 22,963 mld capacities that exist to treat. This brings 76% of the urban cities depends upon the site sanitation, and the government has initiated under various programs to meet this capacity gap in treating the municipal sewage and completed about 20% of the need. On the other hand, there are studies to show that most of the capacities installed are conventional, using chemicals and biological. As per the studies available from Central Pollution Board, it is seen not all the treatment capacities installed are operating at an average efficiency of about 66% due to technological and operational disadvantages. This adds additional burden to the government to the Clean India policy. In industrial front, the reports shows that there is about 501 mld of industrial wastewater is generated and treated. The reports also suggest that our annual water demand in 2030 is estimated at 1.5 trillion cubic meter, and per capita of water resources is projected to dwindle to 1,100 cubic meter per year in 2050 from 1,800 cubic meter per year what was 2001. This leads to reduce the waste by recycling and reuse it. It is at this scenario that PRAALTER has decided to launch this company to bring new green solutions to bridge the technology which is efficient and cost-driven. As per slide followed, PRAALTER is consciously aware of the difficulties in bringing such change against odds and desires to remain as a research and development company as its prime business objective and goal. Founded in 2019 as a start-up company by a group of hardcore scientists and professionals from the advanced countries, joined together with the desire and urge in returning to their motherland, bringing their expertise and knowledge to bridge the technology gap under the Make in India policy. To start with, we will be targeting our technology in three segments: 1. Municipal sewage treatment. 2. Industrial wastewater treatment. 3. Domestic water. In municipal sewage treatment, besides municipal sewage treatment facility mostly run by the government, in view of the capital expenditure and terrain constraint on the government in sewage networking, we anticipate more emphasis will be laid on FSSM septage management and online treatment. We are ready to meet such business opportunities. We have experience and expertise in treating and recycling of industrial wastewater and have executed projects with the capacity of 60 mld elsewhere in the other part of world, when associated with our technology partners. Our expertise includes for industries like textile, tannery, food, common domestic waste, and industrial waste. food and beverage industry, chemical, oil and gas, so on. In oil and gas sector and potable water requirements, we have provided process, design and engineering. H2O Canada implementing silicon carbide membrane technology. Electrocoagulation, a chemical-free process destabilizing the suspended solids, emulsified or dissolved contaminants in an aqueous medium by introducing electrical current into the medium, which provides electromotive force causing the chemical reaction. Consists of 3 components: 1. Power source, 2. Reaction chamber, and 3. Electrodes. When wastewater flows through EC reactor, multiple reactions takes place. First, on the surface of anode, metal ions are driven into the water. Secondly, on the surface of the cathode, water hydrolyzes into hydrogen gas and hydroxyl groups. Third, electron flows freely from cathode to anode, which destabilizes the suspended solids and most of the hydroxyls. As the reaction begins, metal ion complex with hydroxyl group and forms large blocks which consist of metal and other components. Suspended solids and most of the hydroxyls are readily entrained into flux because its stabilized surface changes. Finally, hydrogen gas bubbles are separated and lift the flux on the top of the reactor. This cooperative action makes the process easily so effective and efficient. As the water leaves the EC system, it enters the secondary separation tank. Here, the effect of EC reaction is further accelerated. The flux generated in EC system reacts each other and forms into larger flux that settle out separately in water column. Finally, the water leaving the settling tank fed into filtration system using silicon carbide membrane for ultrafiltration and the row membrane process as the design warrants. The key benefits are: removes dissolved metals such as mercury, cadmium, arsenic, chromium, thallium, lead, iron, boron, copper, manganese, cyanide, etc. Reduction in BOD, God, H2S and suspended solids. Removes color dyes, detergent, surfactant. Removes total petroleum hydrocarbon. Removes bacteria, viruses, algae and E. coli. Some of the key advantages are: one-stop multi-contaminant removal, no hazardous chemicals are used. Reduced sludge at about 0.04 kg per cubic meter on dry basis. Reduced footprint to an extent of 40% as no large equipments are involved due to instant treatment reaction. Reduced operating cost of about 40%. The system is suited for applications in municipal and industrial wastewater, oil and gas produced water, mines process water, construction wastewater, power plant process water and pre-treatment of seawater, reverse osmosis treatment. Any difficult to treat water and waste, and recycling of water and wastewater. Silicon carbide membrane filtration. Next generation of cross-flow liquid filtration, engineered from layers of recrystallized silicon carbide, can purify demanding liquid flow at unparalleled levels of efficiency. Next generation of cross-flow liquid filtration, engineered from layers of recrystallized silicon carbide, can purify demanding liquid flow at unparalleled levels of efficiency. Next generation of cross-flow liquid filtration, engineered from layers of recrystallized silicon carbide, can purify demanding liquid flow at unparalleled levels of efficiency. The filtration system consists of tubular silicon carbide ultrafiltration (UF) membranes, where multitubular membranes are housed in pressure vessels. Backwashing of the UF membranes occurs when the transmembrane pressure (TMP) reaches an assigned set point. Backwashing utilizes water from UF permeate tank through pump to provide high-pressure fluid in reverse direction through the membranes. Row membranes are used for further treatment in case of TDS reduction is required.
Okay. Yep. That one will not be using when we're running in dead end mode. Yep. Then we have the two membranes here. Yep. And then the feed comes in the bottom. Yep. Goes out. Yep. Then we have from this line here the redden tape. Yep. And when we're running in dead end mode, we want to have this valve closed.
So we're running in dead end mode. Just to recapture that, the recirculation pump will not be turned on in dead end mode. Okay, so then when you go in dead end mode, this valve is closed. Okay, go ahead. Okay.
And then we have here the redden tape, but in dead end mode, these valves here, like this one, these two, regulating valve will be closed. Okay. So all feed that comes into the unit will be clean water.
So basically what he's saying is when retented, in dead end mode, all the concentrate or retentant gets basically trapped in that circle right there. Nothing's leaving because recirculation, that's closed and that's closed. Everything gets trapped, so like all the feed that comes in basically leaves as permeate, which is right on the side of here.
Permeate comes.
So the recovery is 100% in dead end mode.
Yeah, exactly. Right. And it comes out here from the side of the membrane. Go all the way down here. On this side here.
So like permeates goes all the way here. Okay.
Then we have the permeate pressure here. Yep. We have a sampling valve here.
Sampling valve, yeah, okay.
For the permeate.
Yep.
And then it goes around here. Through this valve that will be open.
Okay, yeah, the permeate isolating valve over there, so it'll be open on and off, so it's the open valve, okay, yep.
And then on the other side of this tank, we have like the permeate flow meter.
Permeate flow meter is right over there, as you can see it, okay, yep.
And then the water will go up here.
Yep, permeate clean water goes there.
Through this regulating valve.
Regulating valve only for back pressure, correct?
Yep.
So will that be assigned? Like, how do you know how much it should regulate?
It will be in dead end mode.
Yeah.
Yeah, it will regulate itself, of course.
Yeah.
To have like a little bit of effect.
But you don't have to input a value into the PLC? No? So it'll regulate itself?
Yeah. Okay. And then the permeate comes into this permeate tank here.
The permeate will come in.
Then it will be running from the pipe here.
So it comes
down and into the button here.
Wait, oh, okay. So it comes from here, goes there. Oh yeah, okay, I see it. Yeah. The bottom and enters the permeate tank. Okay, cool.
Yeah. And we'll go out here and back.
So can you explain this thing again? These two. So this just gets the air out of the permeate tank, correct?
This one here is for getting the air out of the permeate tank. Yeah.
Okay, yeah.
And the permeate tank we are using for when we're doing a backwash.
Yep.
We're cleaning backwash through the membrane.
Yep.
And then get it out on the concentrate line.
So this is basically permeate line. Now going back to this place, okay, so the transmembrane pressure will be calculated from, this is the feed pressure transmitter. It uses the feed transmitter, it uses the permeate transmitter, and also the retented concentrate. So it uses these three transmitters to calculate the TMP,
yeah,
correct?
You say the feed pressure here.
Yep.
Plus the retented pressure.
Yep. Divided by 2.
Divided by 2 minus the permeate pressure.
And so basically then gives you the TMP right somewhere in the center of
in the middle, yeah.
Middle of the membrane. Okay. The permeate line. This is again. So when you're sampling, you sample the feed from. Where would you sample the feed from?
The feed sample is over here. It's here.
Okay.
This one.
Yep. And then the permeate sample would be here.
Oh,
sorry, concentrates.
Yeah. And the permeate sample is on the back.
Yeah. So when you're doing a test, you typically you sample all three, right? When you're sampling,
yeah.
Kind of know the difference between what you're getting out.
You want to have a feed sample before you start the test, and then you want to have like permeate sample and retentate sample.
Yeah, and then this is just basically a pressure safety valve, which is already assigned a specific pressure. When if there's excess pressure in the system for whatever reason, this opens up.
The key characteristics of the SiC membranes are: it is thermal and chemical resistance, corrosion resistance, excellent oil-water separation characteristics, unmatched physical barrier preventing any suspended solids to pass through. Advantage. The key advantage is that system removes TSS, coagulated metals, bacteria, viruses, residual oil, and BTEX with an estimated 95% permeate recovery and 5% concentrate reject, besides other operational advantage of 30% reduction in chemicals, 70% in backwash water, 20% in power and 40% in turbidity. In addition, it is automated, simple to operate, low maintenance, longer membrane life cycle of 15 to 20 years and risk-free due to high physical barrier of membrane preventing any suspended and other contaminants to pass through permit. Application. The system suited for applications: municipal and industrial wastewater, oil and gas produced water, mines process water, construction wastewater, power plant process water and pre-treatment of seawater, reverse osmosis treatment. Any difficult to treat water and waste and recycling of water and wastewater and personal application for swimming pool. Core team. Mr. Santhanam, whole-time Director and Chief Operating Officer, is an electrical engineer with 48 years domestic and international experience at a senior level management, brings multidiscipline experience from green venture, horizontal and vertical integration and corporate strategy. Dr. Shuva Rao, whole-time and technical director, is a doctorate in water and wastewater treatment science. She was a part of ECR and SiC development with our technology for partners. Her experience includes with GE in their membrane business and underwent training in South Korea in membrane technology. She has published, presented 10+ papers on advances in wastewater treatment, reuse and recycling, removal of contaminant and urban water management. She is also a member of American Water Works Association and certified auditor in OSHA, Environmental Risk Management. Dr. Ing Srikanth, a research scientist in electrochemical energy, specializes reversible energy storage using SOFC technology. Developed technology for the production of synthetic gas from sustainable resources, which shall be used as fuel for generation of green energy generation. Advises us on waste-to-energy business strategy. Dr. Bhargavi Kulkarni carries a Master's in Environmental Engineering with advanced postgraduate diploma in renewable energy. Currently researcher in municipal solid waste. Raghavi P. B. Chartered Accountant with a MCET diploma in Treasury. certified in financial modeling, wealth management and valuation in private equity, guiding us on financial strategy.